Okay, it's my great pleasure now to introduce Professor Aurélien Garivier. He is from École Normale Supérieure de Lyon. Sorry, apologies for the pronunciation. And he's been doing a great deal of work in learning and sequential learning and estimation. And some of the papers that I've read, you see deep, insightful, beautiful work. So we are extremely pleased to have him here today. Look forward to you.
Thank you very much for the invitation. I think you can hear me. And actually, thanks for inviting me to this workshop. I will actually be speaking about probability and optimization at the same time. A very special point of view that takes its origin actually in some work by Sandeep and others here in India. And namely, we will consider, or should I? Oh, it did work. Or maybe I lost the focus here, probably. Yes, that's it. So we will be speaking about optimization of a function that is a black box. So a black box is a function for which you can control some part of the input, but there's also a random input. That's where the probability will come in that determines the output. So our function f will be a function defined on a state of controlled variables. It will be denoted by x times a random space, omega. And we will denote by small f of x the expectation of f of x with respect to the random part of it. And the goal is to optimize f, that is to say, to find the point in x that maximizes the value of f. So typically in the sequel, we will consider the noise to be additive, that is to say, our f of x and w and omega will be the sum of f of x plus some epsilon of omega. And typically, we will take a Gaussian noise, but this is just for the convenience of this introductory talk. Okay, so we will consider the following framework. In the black box interaction model, we first pick a point, x1, at random, like we want, according to some external randomization u1 and some own strategy phi1. And then we observe y1 equals f of x1 and some omega 1. Then, according to what we have seen in the first step, we may choose our second observation point and observe a second value, and so on. And our target in this talk will be to maximize the function f star. So of course, we could have other targets, but for this talk, we will focus on simply maximizing it. And what are our degrees of freedom? So what we can choose is a sampling rule phi sub t. So at every step, what next point we want to choose, and the stopping time tau, because we will say at some point, okay, I have seen enough. Now I'm able to produce something that is close to the maximum of the function. And namely, we will be working in the PAC setting, so probably approximately correct setting. That is, we fix the risk delta and the tolerance epsilon. And when we say I stop, we want to be able to produce a point that is epsilon optimal, so within epsilon from the maximum of the function, with high probability. So the probability that our point is not epsilon optimal is smaller than the risk we fix delta. This is the problem we are considering. And we will denote by x epsilon of f, the set of epsilon optimal points. And our goal will be to design strategies that are epsilon delta PAC, but also that are minimizing the expectation of the stopping time. They're stopping as early as possible. So that's the setting. It's a complicated setting. Our goal will be to identify the complexity of the problem, that is to say, the best possible expectation of tau that one can reach for any choice of a sampling rule and of a stopping time. And in fact, in general, for general functions, it's something that is quite ambitious. So we will consider this task progressively. We will start with very, very simple functions f and make it a bit more complex step after step. Yes, sorry.
Can you just clarify that EF tau is
this one?
EF tau. Expectation.
The expectation, though, if the true function is f of the stopping time tau, okay, should be as small as possible. So yes, I will subscript P as a probability symbol and E the expectation symbol by the function we are using, because there will be change of measures all the time.
Omega 2 or from some.
Sorry?
Omega 1, omega 2.
Yes, so they are from the probability stubs. They are the input here. They are the randomization. Okay, but we will start by some probability actually, and very simple things. So I'm sure that at the beginning everyone knows what I will be presenting, and the way I'll present it will prepare for the future and make it a bit more original. So what I start with is Chernov's bound. Chernov's bound for Bernoulli variables. So I hope you all know that. If you have independent Bernoulli variables parameter mu, and you call x n bar the empirical average, then the probability that the empirical average is a lot larger than the expectation, so we take x larger than the expectation, is exponentially small, and the rate in the exponential can be computed by Chernov's method, and it appears to be a Kullback-Leibler divergence. Okay, so this function that appears as a rate function here in this deviation is the binary relative entropy. Same for left deviations. So I guess everyone knows this. I still recall how to prove it. Actually, it's all in there. It's just Markov's inequality applied after an exponential chain, an exponential mapping, and an optimization on the coefficient in the exponential. So this Kullback-Leibler divergence, yes, the Kullback-Leibler divergence actually between the Bernoulli variable of parameter x and the Bernoulli of parameter mu is a quantity, an information theoretical quantity that will appear very often in the sequel, and generally speaking, it's defined like this. It's you can recall a pseudo distance, a divergence between probability distributions. It has the property that it is always non-negative and equal to 0 if and only if p equals q. So it's a relative distance in a way, even if it's not a distance. Okay, now is this inequality tight? Is it a good inequality that we obtain simply by Markov like this? Well, actually, yes, if you consider it at a logarithmic scale. Okay, so let me go back. Yes. Lower bound. What if we want to lower bound this quantity, p mu, that x n bar is larger than x, larger than, well, we would like e to the minus kl of x and mu. But that we can't reach. Actually, it's not true, but it's still possible to obtain a lower bound of the same flavor, exponential minus n kl of x plus a small epsilon and mu plus a small alpha times something that goes to 1 when n goes to infinity. So it's a kind of reciprocal inequality. And how do we get this? So here, the standard method for those lower bounds in large deviation principles is the change of measure ID. It amounts to saying, okay, under parameter mu, the event x n bar larger than x has a small probability, but under the parameter x plus epsilon, so if the true mean of all the observations were x plus epsilon, then it would be a very typical event, something with a large probability. And the probability of an event under p mu and under p x plus epsilon, it's not incomparable. I just have to correct for the ratio of probability between the two. So I write my probability as the expectation of the indicator, and then I change measure here by introducing the log, the likelihood ratio here, and writing it in a an additive form by the exponential. I find that it looks like a sum of independent variables. So it's a quantity that is quite predictable in what it will be like. It will be equal approximately to n times the expectation of one of those terms here. And n times the expectation of one of those terms here is precisely the Kullback-Leibler divergence of x plus epsilon to mu. So working just a little, but everything is explicitly written on this slide. This change of measure argument is the standard way to obtain an asymptotic counterpart for the upper bound of Chernoff that shows its asymptotic optimality in the sense that by letting epsilon and alpha go to 0 and n go to infinity, we obtain that the limit of 1 over n times the log probability does go to minus KL, that is to say, inequality here, this KL is the optimal coefficient that we can obtain. Okay, and joining the upper bound and the lower bound, combining them, we have proved that 1 over n log probability tends to minus KL of x and mu, which is probably the simplest example of a large deviation principle. Now, I showed you that because there is another way to derive a lower bound than this change of measure argument. And this other way is an informational way, just manipulating Kullback-Leibler divergence. In a way, it's the same thing, but hidden within information theoretical notation. We start from here. We consider, so I wrote with a double bar here, the Bernoulli distribution tensor n, so the distribution of the n independent variables, here, Bernoulli variables, here with parameter x plus epsilon, and here with parameter mu. And we compute in two different ways the KL divergence between those two measures. So first, by using that KL divergence is additive with respect to product measures, we have a simple expression that this is equal to n times the KL of x plus epsilon and mu. And then there's another important property of KL divergence, it's the data processing inequality that everyone knows in information theory. That is to say, if you take the push forward measure of the two members of the KL, you can only reduce the divergence. So here I choose as a mapping the indicator that x n bar is larger than x. And I apply my inequality, and then I obtain measures here. So here you have to understand push forward measure by this function of this measure. So it's the image is 0, 1. It's a Bernoulli distribution. Bernoulli distribution with parameters, the probability that x n bar is larger than x under p x plus epsilon and under p mu. So this is just a binary entropy divergence here. And this binary entropy divergence, I can lower bound it by a simple inequality. So if I look at those terms, this one is close to 1, and this one is close to 0. This is my deviation probability, and this is my typical event. Okay? So I can use a simple lower bound in that case that is very elementary to prove that the scale of P and Q is almost P log 1 over Q, so up to a minus. Thank you. So I'm not claiming that this is the best inequality and the most interesting we can get for this problem, especially for Bernoulli, but just that there is a very simple and generic way to prove lower bounds that we will use in many different settings that is very practical in this, and that is an alternative to the change of measure argument. So for example, if you know about bandits, you know the Lie and Robbins law, lower bound for regret. Well, we can prove more simply the Lie and Robbins lower bounds for regret using such arguments. So now we have considered these reminders. We can start our optimization program, so our black box here. And as I told you, we'll start with this very gentle, in a very gentle way, where we have a function on x, where x is just a 2-point set, 0 and 1. Okay, and we have to find the value between f of 0 and f of 1, which is the largest. And in fact, it's even still too complicated. We assume that we know f of 0. F of 0 is equal to 0. We just have some uncertainty about f of 1. We don't know if it's larger or smaller than 0. So f of 1 is a Gaussian variable with mean mu and variance sigma squared. So in that case, we don't have much hesitation about what points to observe. We always observe xt equals 1, okay? And we should stop as soon as we are pretty sure that, well, either mu is smaller than epsilon, in which case we should output 0, or mu is larger than minus epsilon. In that case, we should output 1. So it's a testing problem, but non-classical in the sense that the two hypotheses overlap. Well, my claim is that overlapping hypothesis is the right way to consider testing, even if it's not what is done in general. But here it appears clearly. So if mu is actually between minus epsilon and epsilon, we don't care what we answer. We can answer either 0 or 1. The two answers are correct. And the question is, how many samples do we need to do this, to find out if mu is like this or like that? Well, we can compute it pretty exactly. We have the following result. For every epsilon delta pack strategy, the expectation of under mu of tau delta has to be larger than 2 sigma squared divided by absolute value of mu plus epsilon squared times log 1 over delta. It's an asymptotic result. So this is true only when delta goes to 0. We will see why. And besides, there is a strategy that reaches this lower bound, a simple strategy, namely one that has a simple interpretation we will see. But for the time being, we can only remind that the lim sup of the expectation of the same thing here is actually smaller than the complexity. Thus, in that sense, the algorithm is asymptotically optimal, and we have determined the exact complexity of this optimization problem, which is equal to this term here. So how do we get such a bound? Well, in fact, the idea will be systematically change of measure. So we cannot stop before we have an alternative hypothesis that is sufficiently likely to produce the data. So as we will call for every function f, we will call alt of f during the entire talk, the set of functions for which the optimal points of f is not included in the optimal points of J. So in that case, it means that if mu is larger than epsilon, the alternative of mu, the function f is identified to mu in that case, is infinity minus epsilon, because in that case, we shouldn't answer negative. And similarly, if mu is smaller than epsilon, we shouldn't answer positive. And if mu is between minus epsilon and plus epsilon, the alternative set is the union of those two sets. So here, any answer is correct, but there are, still the alt of mu is defined like this. So I'm not claiming that the intersection of the optimal sets is empty. That's the definition. And how do we prove the lower bound? We will prove it, well, by change of measures argument, just like in our lower bound we had in the deviation bound originally. And as you will see, as we have seen, indeed, there are two ways to write this change of measure argument. The low, what we call the low-level form and the high-level form. So the low-level form is exactly the way I first wrote the change of measure, by relating the probability of an event under probability under log G to the probability under another parameter f, and we had to correct for a probability that the log likelihood ratio was too high, and times exponential minus this log likelihood ratio. So here we recognize very summarized the slide that we had on the change of measure initially. And the high-level form is the one that was manipulating directly KL divergence. It says that the KL divergence of my observation up to time tau under parameter f and j, well, the expectation of this, which can be simply computed, is by contraction larger than the probability of an event C under F as the KL of, between the probability of under F and probability under G. Actually, the proof of those two lemmas, we have already seen it in the preparatory work here, but it's summarized, rewritten in a way, in a generic way, not specific to Bernoulli variables and deviation probability. And in our case, how does it translate? Well, it permits to show that actually when this term, the expectation of the log likelihood ratio, it's just the expectation of tau, the kind of Wald lemma, times the KL divergence of between the two observations. And you know that between quotients, the KL divergence is just the squared, like this. So the high-level form rewrites like this. And it directly gives a lower bound for the case where mu is smaller than minus epsilon or mu larger than epsilon. Because we can take, in that case, lambda equals epsilon. C, the event we consider is that we answer positive. So we answer that 1 is the optimal point, which is incorrect under mu and correct under lambda. So it has probability smaller than delta under mu and larger than 1 minus delta under C. And we get the lower bound, that the expectation of tau times this square here is larger than the KL of delta to minus delta, which is of order log 1 over delta. So actually, this proves the first, this proves this inequality just for the case where mu is smaller than minus epsilon or larger than plus epsilon, but it proves it in a totally non-asymptotic way. The inequality is true in that case. Asymptotic inequality is necessary for the case where mu is between minus epsilon and epsilon. This will be my first question to the audience, actually. Can you prove this inequality for the case mu between minus epsilon and plus epsilon by using the high-level form? We were never able to do it. We always had to dig into this low-level change of measure. And the consequence is that we only get asymptotic bounds, asymptotic lower bounds, which is a bit of a pain. So it appears empirically that actually the lower bound is not true exactly for mu between minus epsilon and epsilon. We expect that there is something that depends on delta here, non-trivial. But still, we are very interested in trying to get rid of this awful low-level proof in the case where mu is between minus epsilon and plus epsilon. Now, the strategy. How do we reach this optimal complexity? Well, there are two ways to see it. The simplest way probably is the graphical one. So imagine we consider the random walk whose increments are the observations of our unknown arms. So it's a biased random walk, okay, more or less a Brownian motion, okay, a discretized Brownian motion with either a drift that is positive or a drift that is negative. We don't know. So if it's larger than mu, the drift will be larger than the drift under parameter epsilon, so here. And if mu is smaller than minus epsilon, the drift will be smaller than this drift here. So how to make the difference simply, and how to know if we are in the case where the drift is like this or the drift is like that. So we can simply construct a confidence region for both cases. So here I have the confidence interval, say, for any random walk that has a drift below this curve here. Here I write minus epsilon times t plus square root of t times the variance. So I have something that grows like this. And similarly, this is a lower bound for the random walk if the parameter is indeed larger than plus epsilon. So my procedure will be very simple. It will see the random walk, and as soon as it gets out of one of the two boundaries like this, we stop, okay? And if actually mu is smaller than minus epsilon, the probability that we ever get above this curve will be smaller than delta. That's how we construct it. And similarly, if the drift is above plus epsilon, probability to go below this curve will be smaller than delta. So our stopping time will simply be the first moment when we go either below this curve or above this curve. So this will be for sure before the time where they meet here, because after that they have an empty intersection. And we can prove that on average, this will happen approximately here. So when a typical run going up will cross this upper curve here. And when we compute this moment here, we find that it is exactly sigma squared log 1 over delta divided by 2 epsilon. And so we just need to upper bound the probability that it is larger, related actually to a probability of deviation for xn bar. It means that, okay, if the drift is actually larger than epsilon and we are not finished at that time, it means that our xn bar is larger than it should. And this will happen with smaller and smaller probability, and so we will upper bound the probability like this. So this is the first way to see it. The other way, a statistical way to see it, is to consider a generalized likelihood ratio test. So if you write the statistic of the generalized likelihood ratio test, you obtain it like this. And actually what you get is exactly the same procedure. It's strictly equivalent to what I explained before. This is the same test. And it will stop at the same moment. And we can study the properties of this sequential GLRT. And as I told you, we can prove quite reasonably simply that the expectation of the stopping time will be smaller than the complexity term here. So in a way, this simplistic problem, 1.5 armed bandit, is solved, and we have exactly the complexity. Now, can we go further? So further would be to consider now a plain vanilla bandit model. That is to say, a problem of optimization where the set of arms is discrete and there is no structure, okay? No relation between the parameters. So this is what the situation looks like. You have Gaussians, they have some means, and you would like to find the one with the largest mean. So you may sample like you want from any of them. So probably you will sample a lot the largest one. If one is really smaller than the others, you don't need to sample it as much as the others before you stop. The question is, how do you do it optimally? There are lots of ideas that have been proposed, and for example, the racing strategy is probably intuitively the most simple. So you can keep confidence intervals for the value of the function at every point. And as soon as you have an arm for which the upper bound of the confidence interval is smaller than the lower bound of another confidence interval, you know that this one is not optimal and that you can forget it. Okay, so in the first time for the moment, I will consider the case epsilon equals 0. So I really want to find the arm with the highest mean and not an epsilon optimal, just to make this simple. So this racing strategy, I explained how to eliminate arms, and now I have to specify how I sample the arms, so it's not complicated. There are different propositions, but you can think that for such algorithms, you can prove that they are delta correct if you tune the confidence intervals correctly, and you can even find upper bounds on the complexity related to the gaps between the arms, that is to say, the distance between f of x and f and the optimal value of f. Yes. Actually, so these are ideas, and there were bounds and algorithms studied like this. But what we wanted to do with Emily in that case, that dates back to 2016, was to find really the complexity of this problem. And we could prove the theorem, the following theorem, that the expectation of tau for any delta correct algorithm, so there's no epsilon here, is larger than log 1 over delta, say, times some function some t star of the function f, where t star of f is a property of the function that appears to be the solution of a min-max problem like this, solution of a kind of a game. Okay, and let's see how to prove and how to get such a result. And then we will see that just as before, this complexity can be reached, so that this is really the complexity of best arm identification in vanilla bandit problems. Here we will apply the entropic lower bound, the high level entropic lower bound method, which says in that case that so the KL of the observation from time 1 to time tau can be written as so still our Wald lemma, sum of the expectation of the number of times I draw x times the distance from f to j at x, and that this thing is larger, just as before, than KL of 1 minus delta and delta if j is in the alternative of f, that is to say, if they don't have here the same optimal. So this is exactly the same idea as we had used before, but just with many arms. And now, if we apply this change of measure method, we can have a first idea how to apply it to obtain the first lower bound on the complexity. How does it go? So if I take a point A that is suboptimal, well, I change the problem, I make it optimal. So I change f of A, I change f to j by defining j of A to be f star, so that it is optimal now, and it doesn't have the same optimal points as function f, or f star plus epsilon if you want. Yes? Here? This one? Oh, okay, so I went a bit fast behind this, so there's a martingale argument and stopping time behind it, but morally, it's a tensorization property, that the KL of a product measure is the sum of the KL. Okay, just here, the number of observations of each arm is random. So this is the KL of a Gaussian. Yeah. Yes, I'm still in the Gaussian setting. Yes. Okay, so now if I want to change, if I want to lower bound on the number of times I draw arm A, well, I make it optimal. So I build J so that J of A now is optimal by changing just the value of F at this point A. And I apply the previous lower bound, and I obtain the expectation of NA of tau times F of A minus F star squared divided by 2 sigma squared is larger than log 1 over delta. And similarly, for the optimal point, I can make it suboptimal by changing it to any other point and obtain the same kind of thing. So that now if I sum on all the arms, and I sum the expectation of the number of draws of arm X up to time tau, well, when they sum to the expectation of the stopping time, to the total number of observation. And when I sum those lower bounds, I obtain that they are larger than the sum over X of 2 sigma squared divided by the gap delta X squared times log 1 over delta. So this was the kind of bounds we were previously able to obtain. The problem is that those bounds are not optimal because we are doing the changes of measure independently. So the good idea to really identify the optimal complexity of this problem was to combine those inequalities. So we can make mu2 suboptimal by changing mu1 and mu2 to some m2 and swapping them in that way. And that's how we get the first inequality. But we can change mu3 or we can change with mu4. So for all of these points, we have this inequality that we've seen before. So actually, this inequality is true for the infimum on J of this. The infimum of these quantities is larger than KL of delta 1 minus delta. It took us months to combine them, but just writing this infimum here. And once it was done, it remains only to multiply and divide by the expectation of tau here, and to realize that those quantities, they sum to 1, and then to lower bound, to upper bound this quantity by the supremum over omega to obtain something that doesn't depend on the algorithm anymore. And now that we have written this, well, we have our lower bound. We have proved that the expectation of tau times something that only depends on the function f is larger than log 1 over delta. So this is how to get this, this lower bound. Yes, and it can be related, in fact, to the naive bound we have obtained like this. So actually, this T star of f, it is always larger than the upper bound we had by the naive method. Okay, we have improved the naive method, but we can prove simply that it is at most twice larger in the Gaussian case. So it's not at all true in other models. Here I focus on the Gaussian case just for the clarity, but the arguments extend to general one-parameter exponential families with no difficulty. Just in the Gaussian case, one can prove that actually the gap bound is correct up to a factor 2 only. And well, this extends to pack optimization. So that is to say, when we only want to find epsilon optimal arms, then we get a result that is similar, except that again, the fact that we have several possible correct answers now changes our lower bound to an asymptotic lower bound. And the technique is no longer the high level, but the low level form. We are obliged to use it, and we are sorry for that. So apart from this, we get a result that is pretty similar. The limit of exponential tau divided by log 1 over delta is larger than a complexity term. It's no longer T star of f, it's T star epsilon of f, because there's a small epsilon showing up in the optimization problem that we have here. Now, how to reach those complexity terms? Well, again, the way to obtain an optimal procedure from that is to use a GLRT stopping rule. The GLRT, we can compute it in that case. It looks like this. It's the first moment when we have such an expression. Okay, I won't go into it. It has a simple explanation. It has several simple interpretations, indeed, that we express in our 2016 paper. But what you should only remember is that, well, choosing correctly a threshold here for the GLRT, we can prove that we built a procedure that is probably approximately correct. And now how to sample. So we had the stopping rule, we need the sampling rule. Well, actually, what is pretty unexpected and interesting is that our law bound, this one, does not only furnish the complexity of the problem, but it also tells you how to solve it. When you read it a bit more carefully, you see that in the proof at some point, yes, here, we replaced the expectation of nx of tau divided by EF of tau by a supremum over omega. So if we want to reach the supremum here, we have to make an algorithm that for which the proportion of draws of each arm respect the omega here that are the solution of the optimal program. And this suggests the algorithm that we call the track and stop. So track and stop has a sampling strategy that just amounts to estimate at every time what is the complexity of the problem by solving the optimization problem. So finding the omega star for the estimated problem, and then track the optimal proportion for this thing. And if everything goes well, so our estimates of each of the values f of x will converge to the right value. So we can prove the continuity of the optimal weights with respect to those values. And if we track them, we can prove that the limiting frequency of draws of each arm will indeed tend to the optimal frequency that we are searching, and hence that our algorithm will be optimal. So combining the two, this permits to show that our track and stop strategy has a complexity that tends to the expectation of to T star of f. So we can do some experiments and indeed obtain that it does better than the racing algorithm, for example, that I showed you before. But now, in the 5 or 6 minutes that I have left, I wanted to show you now how to go a little beyond the vanilla bounded problem and to include some structure. Our final goal is still to optimize continuous function, but we will still have one intermediate step, and this intermediate step will be to do maximization this time on a function defined on a graph with a graph smoothness condition. So a graph, we have already seen plenty of them today. They have an adjacency matrix, which I denote by W. And I will call S of F the smoothness for the graph G of F, which is a quantity. So it's L2 norm under the Laplacian of F. We will assume that it's smaller than R. That means that for points X and Y that are strongly related by the graph, so if the weight between X and Y is large, we assume that f of X is not very different from f of Y. The sum of the squared differences of the values between 2 points that are related has to be smaller than R. So this implies that your function is smooth with respect to the structure of the graph. Okay? So if 2 points here, X and Y are close, their values have to be different, have not to be too different. And well, in that case, the set of functions we are considering is the set of all functions on the k points, the k vertices of the graph, for which we have this constraint, this smoothness constraint, and we can prove similar results on the expectation of the stopping time of any delta correct strategy, very similar to what we had before, just an expression that is a bit particular for the alternative set here. We have to restrict to a set of functions that are R smooth. And this has been extended to pack optimization. So when we have an epsilon and we are okay with epsilon correct answer. Computing the complexity term in that case is not very is not as straightforward as in the previous case. So computing the max mean problem is not completely trivial, but we have a mirror ascent algorithm in the paper that explains how to do it pretty efficiently. That is at a rate that we control. So for optimization, from an optimization point of view, is a slow rate, but for us it is sufficient to what are our needs. The algorithm looks like this, so maybe I don't have to go into the details now. And we can prove that indeed, well, there was no state of the art for this problem, but we could compare the empirical complexity we found with the theoretical view and show that there is a good match between the two. Now, let's conclude with what we were initially interested in, that is to say, what if we have a continuous function? Well, in that case, we may discretize the function, and then we have a graph. If the function is R2, say it's a grid. And we may encode the regularity of the function f in different ways. The first idea might be to consider that it is Lipschitz. In that case, two points that are close have a difference of values that is bounded by a fixed value. The second idea is to have such an energy condition, which is exactly the limit when the grid gets more fine and fine of the graph regularity condition we had before. Okay, we were summing the squared norm of f of x minus f of a minus f of b. So when we take the limit a and b going to 0 and rescale correctly, what we get is a constraint on the integral of the squared norm of the gradient of f. Okay, so the class of function we are considering we can consider this kind of function, and when we discretize, we obtain a result that is we obtain a graph problem with a graph constraint just as the one we had seen before. And the question is, okay, so we can apply our algorithm, but what happens to our algorithm? What happens to the complexity when the grid gets finer and finer? Can we find a limit? And what can we say on? So we had said that our algorithm was associated with an optimal frequency of draws of each point. So that's what I was saying here. That the omega stars, the omegas in the realizing the maximum here correspond to optimal frequency of draws of all the arms. So how does it translate in the continuous case? Do we see an optimal frequency of draws appearing on the grid that would have some kind of property of convergence when we go to the limit, and that might lead to an optimal density of draws that would be necessary to identify as soon as possible the maximum of the function in a continuous setting? So that is still a work in progress. In fact, we don't know. We have made some numerical experiments on this, but we have no theory so far that permits to really show what happens in the case of a refined grid. We have some results that are encouraging and some not. For example, this is a simulation where we have a function, and these are the optimal weights, and we see that there seems to be a delta mass and the maximum in the limit, which is not what we would like to see, of course. Okay, well, and that will be my last word. So thanks for your attention. Yes. Can you repeat a little louder?
So these information theoretic lower bounds can be used even in the non-sequential setting, right? In the fixed budget setting.
Okay. Yes, in a batch setting, it's very interesting. So here I proposed everything in a sequential setting, but actually, what could be said even from for this problem, for this simple testing problem, here in a batch setting? So actually, yes, the lower bound technique with the change of measure applies and leads the same quantity. But this quantity is not optimal in the batch case. It's not optimal by a factor 4. I can show you. In that case, for example, well, if you just consider the simple testing problem, mu equals epsilon versus mu equals minus epsilon, you can compute the Niemann percentage test and look exactly at its complexity. You will find that its complexity, it's 8 times sigma squared divided, sorry, it's where is it? Yes, it's here. The true complexity, batch complexity of this problem is this one, whereas the sequential complexity of this problem is that one. And the lower bound we obtain by information is the same for the batch and for the sequential setting, which amounts to saying that this information technique gives the lower bound with the right constant for the sequential setting, but pessimistic lower bound for the batch setting by a factor 4. And I don't know how to informationally, with purely informational theoretical bounds, obtain the true bound for the batch, lower bound for the batch setting. A side message is that in this case, there is a gap of 4 in the number of samples you need between the batch setting and the sequential setting. So you can have the same level of confidence with 4 times fewer observations on average if you allow for a sequential test instead of a batch test. And this graph explains it in a way.
Question, in the last setting, when you had a continuous function, does one need to discretize, or can you just do something in the continuous space, you know, the whole of lower bound analysis and the algorithm?
Yes, I don't know how to tackle it completely generally. So what should be a sampling rule? What should be an alternative in the without discretization? As I showed, I consider this as a progressively complexity improving set of problems, and I was at each step trying to rely on what was done before in order to solve it. So I thought maybe going through discretization and having a grid finite might be lead to the answer, but I don't know. There's maybe a path. I don't know, in fact, if we can address it directly, and that would be very interesting, of course.
Okay, yeah, go ahead.
Yeah, so how does it compare to the exam banded literature, where they assume that the near optimality dimension is very small and they do some adaptive research and so on, right? So how does your graph Laplacian regularity compare to that assumption? So it's not so clear.
Yeah, okay. So it's a pretty different line of work. So some people not caring about lower bounds, but rather on upper bounds, have designed methods like SO, HO, DO, things like algorithms like this that often are based on the sequential partitioning of the space, and for which they obtain guarantees either in terms of regret, simple or accumulated regret, and they express the difficulty of the optimization problem in terms of the near optimality dimension, which counts how much mass there is that is close to optimal. It would be interesting to compare the two settings, but clearly this is a smoothness condition and it doesn't compare to near optimality dimension. In particular, those algorithms that require some regularity just around the maximum, whereas here there's a global, very global smoothness condition. So it doesn't compare directly, but yes, the hope is that the kind of methods we obtain like this are better than those who are, well, those HO and so on are tackling directly the upper bound without having any idea of the lower bound. So it would be a miracle if they could match the lower bound. I would be very happy, but it would really seem like a miracle.
Okay, so the no more questions. Let's thank the speaker again.